Here's a conservation of energy example that I consider to be easy. We have a coaster starting at the top of the hill. The coaster is got an initial velocity of 0. It's on a hill of height h. It's h that we wish to find, and we wish to find it such that when the coaster is at this spot at the top, so right at the top of the hill, we want the coaster to just barely make it through that spot. So, not surprisingly, I'm going to start this with a free body diagram at that spot. So I've got my coaster here. I know that there's mg on the coaster acting down, and there's force of the track acting on the coaster. Now, in the barely make it through, this guy is going to be 0. So there's no force needed from the track to keep it in circular motion. All circular motion comes from that mg. So in that case, and again, we only have one direction that we care about. I'll just say x direction, positive down. And in that case, when I do the sum of the forces in the x direction, I'm going to get mv squared over r. R is my radius of the circle. So that means mg equals mv squared over r. The m's cancel, and I get that, well, v squared is equal to r times g. And I'll save this for a little later. Now what I want to do is come over here to the other side, and I'll do conservation of energy over on this side. Mechanical energy. No friction, so we're going to assume that everything, all the mechanical energy in mgh goes to the top of the loop. Potential energy of gravity equals 0 at this location. So in other words, everywhere along this lower line here, potential energy of gravity is 0. You get to pick that, and when you have these gravity problems, you do have to pick a reference point. I could have picked it up here. I could have done that, but I won't do that because it just changes the signs on the problems and so forth. It won't affect the answer. So I have the condition of mgh, so my before and after, so I'll label this section here before, and this section over here is after. I don't think I have to worry about the bottom of the loop and do it in 2 steps. I can do it in 1 step. So in my before energy, I've got mgh plus 0, v naught equals 0. So no energy from the motion of the cart when I start. And then I'm going to be equal to the after. And I guess I put a little line here to separate them. And in the after case, I've got mg2r, because that's the distance that the coaster is from my reference point. So that's the gravity plus 1/2 mv squared. Now you can see why I wanted this other v squared over here, why this particular equation was important, because I'm going to need it right there. Now the nice thing about this is if you notice all the masses divide out. It doesn't matter what the mass of the car is in this problem. And it's one of the reasons it's an easy problem. So I'm trying to find h. So if I go back here, I'm going to just say there's the thing I'm looking for. So I'll solve for that. H is going to be equal to, let's see, we've got our g2r plus 1/2 v squared, and then I want to divide the whole thing by g. It's the g that's on that mgh initially. And then I want to plug in, you can see that g cancels there. Now I'm going to plug in that v squared. So H is going to be 2R plus, now I plug in the V squared, 1/2 R G over G. There's that G there on the bottom. So those G's cancel. And again, I get 2R plus 1/2 R. So H is going to be 2.5 R. R was given as 5. So that's going to be what, 12? H is going to end up being 12.5 meters. And that's the answer. Have